So now we're going to continue our conversation in Unit 4 on land and water use. The previous chapter, Chapter 12, dealt with land use, forestry, and all that good stuff. And now we're going to look at the freshwater part of land and water use. Okay, freshwater systems and resources. All right. So we are going to look at freshwater distribution on the earth and freshwater systems, how we impact those freshwater systems, issues related to water supply, and try to address those issues. We're going to talk about water pollution and ways to handle water pollution. We're going to talk about treating drinking water and wastewater, as in water you flush down the toilet. So fracking is our case study. The American West has had a lot of water conflicts in farmers, ranchers, and growing cities. One thing that they are doing now is with this idea of fracking. They are drilling shale oil out of the ground and natural gas with that's located in shale rock underground. And that process is called hydraulic fracturing or fracking, because fracking is very water intensive. So fracking, they drill down into the ground, okay, and then drill horizontally, and they put high pressure fracking fluids, which is water-based as well as other chemicals. They pump it down in there. It opens up the rocks. It allows oil and natural gas to come out, and they suck it back up and process it. There's a lot of water that is injected into the well, and the water that comes back up is wastewater. It's full of sand and chemicals that don't have to be disclosed, and it's evaporated from these pits, and then, or it's sent to treatment facilities. The areas where there's a lot of fracking going on, and you can see that with these little light gray dots. There's a lot going on in West Texas, in Oklahoma, in upstate New York, and Pennsylvania, western Pennsylvania, Ohio, West Virginia, not so much in upstate New York. There's a lot of areas that have water stress, okay? So it's arid or low water use or extremely high water use. Texas has a lot of water stress in general. Adding fracking onto it is creating more stress on an already overstressed resource. So if we look at freshwater systems, the vast majority of the earth on the planet, almost 98%, or 97.5%, let's go with 97.5%, is in the oceans. And we can't use it because it's too salty to drink or use for irrigation. We cannot survive on salt water. Only 2.5% of that water on the earth is considered fresh water. So out of all the water on the earth, only 2.5% is fresh water. Okay. Of that 2.5%, 79% of it is frozen. We can't get at it. It's in ice caps and glaciers. 20% is groundwater, so that means that that's water that's down in the ground. If you have a well, that's what you tap into. 1% of that 2.5% is surfaced fresh water, okay? At the surface, water that is not salty. More than half of that is in lakes. Most of the rest of that is in soil moisture or atmospheric water vapor. The amount that's in rivers is the same as the amount of water that is within organisms, which really is not a lot. Okay, we talked about the water cycle in a previous chapter, so we're not going to dwell on that too much. The fact that water cycles through these different parts of the water cycle creates interconnected freshwater and marine aquatic ecosystems. This is really kind of important. What happens in one system affects another, okay? So You've got pesticide that's making its way into groundwater and surface water and fertilizer, which is then going to change the composition of the river or the wetlands or any of it. All of the water is intertwangled. So water runs off the land and makes its way into rivers and creeks and streams, which will then make its way into the ocean. Okay, so everything will make its way eventually into the ocean. Everything is interconnected. Surface water is water at the surface. Thank you, Captain Obvious. Water is water in the ground. Okay, and we've talked about this a lot. Any water that's on the surface that doesn't evaporate or flow, run off into waterways, will eventually percolate down into the ground, into the groundwater. And groundwater has a huge residence time. Okay, it can stay in the underground for thousands of years at a time. So when you have a well, it's tapped into something called an aquifer. It's a sponge-like formation of rock or sand, the upper border of which is the water table. And the water table moves up and down as we pull water out of the aquifer. Okay? The more water we pull out of the aquifer, the lower the water table gets. Any area where the aquifer is close to the surface, right, where the water gets into the aquifer, is called the recharge zone. Confined aquifers, okay, are between two layers of impermeable clay, which then puts pressure on that water, so you get what they call an artesian well. It's a spring, it just, comes up, versus an unconfined aquifer where there's no layer over top. This is a big issue when we talk about water use. The Ogallala Aquifer is the largest aquifer in the world, and it is under the United States, okay, in the Great Plains. So this is where our farming comes from. So we're using this in tremendous amounts for agriculture and for human consumption, right? Municipal and industrial consumption. So it's being withdrawn faster than it can recharge. So this is getting smaller and shallower in some areas, and that's very detrimental to the future existence of water in the Great Plains. So surface water becomes groundwater by infiltration. We talked about this when we talked about the water cycle, so I'm not going to dwell on it too much. We talked about the idea of runoff, and then runoff converges to make streams, which can merge into rivers, which can reach a lake or an ocean. We talked about the watershed. Okay. Oh, apparently we have two slides that are the same. Rivers can shift over the course of time. The area near where a river that floods periodically is called a floodplain. Floodplains are really fertile because they are the flood waters bring nutrients that are at the bottom of the river. Okay, so they're great for agriculture, but they're not good for people because, when your house floods, it's expensive and damaging to your personal belongings. Riparian forests, riparian means riverside, they're especially species rich because of that influx of nutrients. So if we look at characteristics of a watershed, characteristics of a watershed impact the runoff rate, the erosion and vegetation that exists in that watershed. It's the area or the size, the length, the slope, the soil type, and the vegetation. So the size or the area of a watershed can be a reflection of the amount of runoff and what's created by that runoff, rivers, streams, or creeks. It can also determine how the runoff is discharged into a lake or an ocean. And it also talks about how much runoff can be held within the watershed. The bigger the area of the watershed, the more runoff it's going to hold. So length and slope determine the rate of runoff. Slope is change in elevation from here, from the headwaters to the discharge point out here. The bigger the slope, the steeper the angle, the greater the rate of runoff. If it's flatter, if it's a smaller slope, there's less runoff. Okay. The length is the distance between the headwaters and the discharge point. So it determines how long it takes the runoff to reach the discharge. The longer the watershed, the longer the time it takes the runoff to be discharged. Okay. Soil type determines the amount of runoff and the vegetation that exists there. So if the soil is really fertile, more vegetation is going to be there. So then we can talk about that in a minute, the impact of more vegetation. If the soil is sandy or has bigger particles, less material is going to run off. Instead, more is going to be infiltrated. And it can also filter pollutants and stuff in a watershed. The more vegetation that's in a watershed, the less erosion will take place because there are roots, plant roots there to hold the soil in place. And it can also improve soil fertility because as that vegetation dies, it can provide more nutrients into the soil, or it can hold soil nutrients more in place, and it can also filter water. We're not going to really deal too much with lakes and ponds because you've dealt with that when we did the biomes. But these are some, the limnetic, the profundal, and the benthic zone. Okay, oligotrophic versus eutrophic. Okay, oligotrophic lakes and ponds tend to be lower in nutrients and higher in oxygen. Eutrophic is like eutrophication, high nutrient, low oxygen. Okay, we're going to skip this stuff on the bogs and the pools. We negatively impact waterways. I really don't think the next world war is going to be over land. It might be over food, but I think it's really going to be over water. It is renewable, okay, but we are altering the water cycle similar to the way we're altering the carbon cycle. We're withdrawing water at unsustainable levels and depleting surface and groundwater. We have altered natural rivers. About 60% of the world's largest rivers have been altered by dams and canals. So we've changed the natural flow of these river waterways. Water is not evenly distributed, okay? There are areas that have very little water and areas that have quite a bit of water, all right? And there's varying degrees of precipitation across the planet too. So water is one of those precious resources. Human distribution does not match water distribution. So there are areas, the Middle East and Northern Africa, and even places in Southern Africa, like South Africa, that do not have adequate local water supply, which puts stress on the people and the infrastructure there. Most of our freshwater use is for agriculture, okay? 70% is to feed our population. Industry is about 20%, and residential use is only about 10%. So because we are using most of our water for irrigation, that has increased something called consumptive use of aquifers, and surface water. So we're consuming it, but we're not putting it back. We're using it, but it's not going back in. Non-consumptive use, like a dam for power generation, doesn't remove the source, or it removes it temporarily and puts it back. So those are two different kinds of water use. We have altered the Colorado River to the point where it does not reach the Gulf of California. It dries up before it gets there. We've put so much demand on it. So then that changes the ecosystem of the river and the delta south of the dry point. There are some areas where people are mining water, like we're going to talk about mining minerals and ores. We can mine water as well. And it's being mined out faster than it's replenished. And here's your Ogallala Aquifer for one of them. It's happening in Australia too, and parts of China, northern India. So if you look at the Aral Sea, which is right here on the border of Uzbekistan and Kazakhstan, So this was the Aral Sea in 1987, and this is the Aral Sea as of 2018. So they used a lot of that water as irrigation for cotton fields, okay, and cotton production. So they overused it and it dried up. The Aral Sea used to be a great fishing ground, so they've lost fishing jobs, they've lost the cotton production, and now as water ran off into the tributaries that wound up in the Aral Sea, it carried pesticides with it. So now the pesticides have settled to the bottom, the water has evaporated, so as dust blows, it's blowing pesticides all over the desert areas. So this was a ship that was a fishing vessel or some other kind of vessel in the Aral Sea, and now it's stranded. It's there's no sea there anymore. We talked about this. Okay, groundwater is depleted more easily because it takes so long for water to recharge, and we'll do a lab possibly after the AP test to show that. So there are areas of pretty crazy water depletion. As you withdraw water from an aquifer, the water table drops. So you have to go deeper and deeper to get to that water. Some people are actively drilling freshwater wells and selling that water to fracking companies in Texas because it's a valuable commodity. It's a necessity when it comes to fracking. When groundwater is over extracted in coastal areas, okay, fresh water is less dense than salt water, so fresh water will sit on top. As you pull fresh water out of aquifers, that salt water in coastal areas is going to intrude in. They call it saltwater intrusion. And then what winds up happening is your well pulls up salt water instead of fresh water, which is extremely problematic because then you don't have fresh water to drink. As aquifers wind up losing their water in places like Florida and Texas and in places in the Caribbean, because their underlying rock is limestone, the overlying rock collapses because there's no water holding it up. And then that causes something called a sinkhole, which is where big areas of land just suddenly collapse and you're looking down into the deeper parts of the earth. It's probably my biggest fear. Most of our bottled water is groundwater. $160 billion in water sales worldwide in 2015, and that has to have gone up. They buy it for convenience and taste, even though tap water is just as good. It has huge ecological impacts. Besides the water itself, pulling the water coming out of the ground, the energy it takes to bottle and process, it's 1,000 to 2,000 times greater energy impact and energy cost than tap water. Okay? And it creates 1.5 million tons of plastic waste every year from these plastic water bottles. That was one of the biggest things that impacted me when I started teaching this class. Since then, I have been bringing my own refillable water bottles. It's a lot more common of a thing now to have your own water bottle than it was when I started teaching this class. But it's definitely one of those changes that I've made to reduce my impact, because this threw me for a loop. This totally stunned me. So flooding is a natural process. We talked about it at the beginning, where you have snowmelt or excessive rains that cause the river to spill out over its banks onto the floodplain. Long term, okay, floods are a good thing because they spread nutrient-rich sediment all over those floodplains. So then that, allows for better forest growth and agriculture and all that. But if you live in a floodplain and the area floods, then that's damaging to your house. So after Superstorm Sandy came through, if you live in a flood zone, a lot of mortgage issuers, banks required, and insurers, insurance issuing companies required that you build your house up on stilts, or build your house so that the underlying area is garage and storage rather than living space. So in a lot of cases, to protect against floods, they build levees, little walls, higher walls, to prevent waters from flooding. And that was what they did. They do that in Louisiana, around New Orleans, because New Orleans is lower than the Mississippi River level. And when Hurricane Katrina came in, the pumps that normally pump the water out of New Orleans when it rains failed. The power went out and the levees broke. So water came flooding into New Orleans and caused lots of issues that are still there. And Katrina came through in 2005. So an aqueduct, the Romans used aqueducts. It channels water from distant sources to cities or agricultural areas. And this is an aqueduct, the Colorado River Aqueduct, diverts water from the Parker Dam to Los Angeles and San Diego. So a lot of those areas in the desert have water that gets trucked in or aqueducted in from other areas. These aqueducts have allowed California's Central Valley to be really agriculturally productive, right? So almonds and berries and all that stuff. But it's at the sacrifice of other areas having surface water. That's part of the reason why the Colorado River never makes it to the Gulf of California. So a dam is anything that you place in a river or a stream to block its flow or to alter its flow. Typically, dams create reservoirs, which are big artificial lakes. And we're going to talk about this a little bit more when we talk about conventional alternative energy sources in Chapter 20. So putting up dams prevents floods. You get drinking water. It allows for irrigation and allows you to generate electricity. So there are some good things. The green are the good things. The red are the less good things. So there's a small risk, but there is a risk that the dam could fail. And then you have all of this reservoir rushing down. The sediment, because it alters the river flow, the dam alters the river flow, sediment builds up behind the dam and doesn't flow downstream to nourish the floodplain on either side. There's habitat alteration upstream and downstream. This was a river, and now it's basically a big lake. So areas that were not underwater became underwater. And then downstream, the water is shallower. You don't get that flooding. So it alters ecosystems upstream and downstream. If you're downstream, the water is shallower. You don't really get a chance to go tubing and do all of those things. Fisheries are going to decline because, in many cases, because the water is shallower, so it gets warmer. Warmer water does not hold as much dissolved oxygen, so fish tend to not be able to survive as well in these, and they block migration. Okay, you have species of salmon that migrate upstream. They can't migrate upstream with a dam in the middle of the river. Okay, they do build fish ladders to facilitate that, but for the most part, their migration is blocked. It disrupts the flooding that builds the topsoil because all the sediment is back here. And upstream of the dam, in the last 50 years, 40 to 80 million people lost their homes because the river valley got flooded to build a dam. Okay, so those are all the negative sides. Positive sides are the green. You've got new recreational opportunities on the reservoir. So you can charge for entrance. You can charge to bring your boats. If the watershed and the land around the reservoir are protected, it's a good source of drinking water. It's a good source of irrigation water for farming without pulling from aquifers. Downstream, you get flood control. Okay, instead of the river flooding seasonally, which then would build topsoil, you don't have as much downstream flooding because you can control the flow of the river through the dam. All right, because it's a dam, right? You can use the power of that falling water to turn a turbine to generate electricity. As long as the dam is in place, as long as the river levels are high, it's continually renewable. And when you generate electricity this way, you do not have as much carbon emission, okay? So it's a lower environmental impact than some other forms of electricity generation, particularly from using fossil fuels. So the Three Gorges Dam is one of the examples of the dams. There are pros and cons. It cost $39 billion to build, so it was really expensive. It's over a mile across. The reservoir, when they built it, flooded 22 cities and countless amounts of farmland and habitat and displaced 1.25 million people, okay? It also deprived coastal marshes of sediment, so you've impacted coastal ecosystems hundreds of miles, if not thousands of miles away from the dam itself, because there's no sediment supply coming in from the river. So you're changing those ecosystems. There's also some research that suggests that they built the dam in a zone moderately prone to earthquakes. So you can have some issues with all that water sitting over all that rock to cause shifts in the crust. If there is an earthquake and that dam breaks, that's going to be an issue for lots of people downstream because it's a huge dam. What we've seen really is that there's a shift towards dam removal, that removing dams winds up restoring those riparian or riverside ecosystems. You get better fisheries. You wind up with river recreation rather than reservoir recreation. And we've seen a return to more natural coastal habitats once the sediment flow is restored. And there have been about 400 dams removed from the U.S. in the last 10 years. I was witness to one of them right before it closed in 2010 on the Elwha River out in Washington, and we'll talk about that when we talk about our key points. So one thing they're looking at, this was a big, John Muir, who was like the founder of the environmental movement and the conservation movement out in California. He wants to remove this O'Shaughnessy Dam to allow the Hetch Hetchy Valley to return to its normal state. He wrote a lot about the damming of the river in the Hetch Hetchy Valley in the early 1900s, but they went ahead and did it anyway. Now they're looking at removing it. So we have definitely increased our water use over the course of the last 50 years. And, you know, as I said, we're running low on water. It's going to run out eventually. So if we are going to handle those water shortages, we either need to increase supply or we need to reduce demand. Those are really the only two ways to deal with a water shortage. So increasing the supply can be expensive on a number of levels. So desalination or desalinization is when you remove salt from water. You can heat it and evaporate it through distillation, or filter it through membranes with tiny pores that trap the salt. They call that reverse osmosis. And if you read some of your water bottles, they say it's filtered through reverse osmosis, which it's not really fancy. Now you know what it is. It's expensive. It uses a lot of energy because you have to heat that water. And what's left behind is waste, salty waste that you have to deal with. It makes sense that Saudi Arabia gets most of its drinking water from this process because it's Saudi Arabia. They have a whole lot of oil. It's really hot, okay? So it takes less effort and it's less expensive to get drinking water that way because they have the right environment for it. If we look at other ways to reduce our demand, if agriculture is the biggest drain on our fresh water supply, then it makes sense to look there as ways to use water more efficiently. So you can line an irrigation canal. When we talk about irrigation, it'll make sense. So you can line a canal to prevent water from leaking or seeping down into the groundwater, so you're more efficient with that. You can level a field to minimize runoff, or use some of the farming methods that we're going to talk about towards the end of the course to conserve water and reduce runoff. You can move to more efficient methods of irrigation, like drip irrigation, so you can reduce the amount of water that gets lost. And this one makes the most sense. Eliminate water-intensive crops from arid regions. This makes me crazy. Almond trees, okay? Almonds use 10% of the water used in the entire state of California. California is huge. California has a lot of agriculture. 10% of that water is just almonds, because almonds are a water-intensive crop, and California Central Valley is pretty dry naturally, okay? So don't grow almonds in California where there's no water. To me, that makes the most sense. At home, we can use more efficient equipment, right? So we can install low flow toilets, washing machines, shower heads, and faucets, right? To reduce our water use at any given time. Turn off the faucet when you brush your teeth, you know. Don't take a 35-minute shower, take a 15-minute shower if you can. You can also use alternative sources for gardening. So you can harvest rainwater, okay? So you create a rain barrel. Rutgers, by the library in Flemington, does rain barrel workshops where you can make your own rain barrel, and you can collect that water and use that to water your plants. Or you can use gray water. Gray water versus black water. Black water is stuff that you flush down the toilet, okay? You don't want to use that. It's against the law to use that. But you can use water from showers, sinks, washing machines. In some places, you can use that for watering, so you can have, gray water collection system. Something else that they do in California is xeriscaping. They use low-demand native plants, and in some places, if you plant using xeriscaping, right, you're going to get a tax rebate because you don't have to water your front yard as much as somebody who's planted grass. Okay, there's a lot of area that there's water that is in conflict, okay, water that's disputed based on where that water is, and you can kind of see those here. 261 major rivers cross national boundaries. So if, the water that, if there's a country that's closer to the headwaters, they're using a lot more water, then that's going to impact the people downstream towards the discharge point. So people need to cooperate. And it's worked with moderate success, as you can see in this example. So we can impact aquatic ecosystems by introducing toxic substances and microorganisms, okay? So it's more than just the amount of water that we're using, it's how we're treating the water that's there. More than half the world's major rivers remain overdrawn and polluted. So water pollution is any change in chemical, physical, or biological properties of water due to human activities, okay? A lot of those impacts of water pollution are not visible, okay? Like we did in Kingwood Park. We measured pH, we measured nitrate and phosphate, which is nutrient concentration. We measured dissolved oxygen. You can't see that kind of pollution, so you have to test and monitor like we did. There are two main types of water pollution: point source and non-point source. These are, when we talk about air pollution, we're going to talk about these again, okay? Point source pollution is a discrete location that releases water pollution. So a pipe, an outlet, it's coming from one particular area. Non-point source arises from multiple inputs over large areas, farms, streets, neighborhoods. This is a great picture. I would like mark this picture somehow, okay? Point source is on the right, non-point source is on the left. So toxic chemicals, this pipe, the wastewater treatment plant, this pipe, feedlots can be non-point source also. All right, so it's an oil tanker is a specific thing that causes pollution, okay? These are generalized, right? Fertilizers, pesticides, and herbicides from that have run off, okay? You can't pinpoint where they've come from, all right? So these are the kinds of things that you wind up having from non-point source and point source pollution. Super important diagram. I would definitely pay attention to this. So some of those toxic chemicals that can be released into the water: pesticides, petroleum products, arsenic, lead, mercury. We're going to talk about mining runoff, acid mine drainage. Plastic is a huge pollutant that's made its way into our waters. And disease-causing organisms like bacteria, parasites, can wind up getting into drinking water supplies from malfunctions at sewage treatment plants in the developed world or open sewers in the developing world, neither of which are good. These biological pollutants cause more human health problems than any other type of water pollution. So 3,800 children die every day of waterborne diseases: cholera, dysentery, not nice diseases, because they're drinking dirty water. Nutrient pollution, we've talked about that, and eutrophication, so I'm not gonna cause those issues, but it's causing that hypoxia and anoxia, those dead zones that we talked about in the Mississippi River and in Chesapeake Bay. So there it is. Again, we talked about this earlier, oligotrophic versus eutrophic. If there's eutrophication going on, this is what it's going to wind up looking like. Okay. Human inputs from farms, golf courses, lawns, and sewage. So if you over-fertilize the farm, they use a lot of fertilizer on the golf course, which makes it look beautiful. If you put too much fertilizer on your lawn, if you have a malfunctioning wastewater treatment plant, it's going to have eutrophication. It's called cultural eutrophication. It's human-induced or anthropogenic eutrophication, if you really want to be fancy. And there's the dead zone that we talked about. So when you do any clear cutting or mining, or you clear land for development, you wind up having soil erosion, which puts excess sediment in the water, okay? And this is natural, okay? This is a river delta, but because you've had clear cutting upstream, you wind up having issues with excess sediment pollution. If you have water that's coming from a power plant, like a nuclear power plant, that water, we talked about the idea of thermal pollution before when we looked at the pros and cons of dams. That water is going to be too warm, so it doesn't hold enough oxygen. So those fish species and some of the other species won't survive as well. Wastewater, right? Human waste, any of that is biodegradable. As that decomposes, you're going to create the low oxygen situations. Wastewater is any water that we get rid of. Okay. Groundwater is also vulnerable, as groundwater takes a long time. It's got a long residence time. Once that water gets polluted, it's really hard to get it unpolluted. Chemicals don't break down as much because there aren't really microbes down in that water to do that decomposition, and there's no sunlight, so temperatures are lower. And when you withdraw too much groundwater, those pollutants wind up concentrating, so they become more potent. Okay. There's natural pollutants in groundwater, but there's a lot of human introduced pollutants, like underground oil tanks, escaped methane and wastewater from fracking operations. We're gonna talk a little bit more about that. So this is water from a tap that's supposed to be drinkable. I would definitely not want to drink that. So we have dealt with these issues with legislation. This is another piece of legislation that you guys need to know. The Clean Water Act came around in 1977. It's the whole goal of the Clean Water Act is to create water, surface water, that is enjoyable and suitable for recreation and human consumption. Okay, so it set standards for contaminant levels in surface waters. To if it gets above that level, then we test and we fine and we figure all that stuff out. And then it also funded construction of sewage treatment plants. When we go to the wastewater treatment plant, you will see that it's definitely the progression of it started. It really got amped up in the late 70s, early 80s. Okay, one of the biggest success stories of the Clean Water Act is the improvement of the Great Lakes. They've been monitored and remediated tremendously over the course of time. So you see a big increase in the health of that water by a subsequent decrease in pollutants. We also treat our drinking water. It's treated with chemicals to remove any particulate matter to allow it to flock, or that particulate matter to collect together and sink to the bottom. They filter it, they disinfect it with chlorine. So tap water is more regulated than bottled water, which is why drinking tap water it's another reason why drinking tap water is better. So we need to talk about treating wastewater in rural areas like where we are. We use septic systems to separate solids and oils from water, and then it gets pumped out into a septic field where bacteria treat it and deal with it, and it filters through sand before it goes back into the water table. That's what most of us have out here. In urban areas, though, and when we go to the wastewater treatment plant in Three Bridges, you'll see this. That water, if you have a sewer, makes its way to a wastewater treatment facility where there's three levels of treatment. Primary treatment is when the water is physically separated and screened and filtered to remove contaminants. So they'll screen it, they'll clarify it, they'll let the stuff settle out or rise to the top if it's oil. Secondary treatment, they use bacteria to decompose those wastes in it. So they add bacteria to the water, but then they have to kill the bacteria because those bacteria are hazardous to the environment. So through tertiary treatment, they kill bacteria, typically with chlorine, and return it to rivers, lakes, or the ocean. In some cases, the biosolids, the stuff that's left over, can be used as fertilizer. It's against the law in New Jersey to do that. So this is primary treatment, the top part. Secondary treatment are 3 and 4. And then filtering and disinfection is the tertiary treatment, okay? We'll talk in a little bit more detail about this when we do our key points, and we will also definitely see all of this when we go to the wastewater treatment plant. So one thing, as a move to get back to naturally functioning ecosystems as a way of sustainability, engineers have worked to construct new wetlands or manipulate pre-existing wetlands to do primary and secondary treatment rather than use the wastewater treatment plant. So to let the natural ecosystem services that exist in wastelands, the natural bacterial decomposition, do their thing to clean wastewater to allow it to go more quickly back down into the ground. All right, so there is freshwater use.